In this video, we're going to learn about the rational root theorem. The rational root theorem states that if you have a polynomial with integer coefficients, then there are a limited number of possible roots for that polynomial. Ideally, integer roots must be factors of the constant term at the end of the polynomial with no x, and rational roots must be of the reduced form of p over q, where p is an integer factor of the constant term, and q is an integer factor of the leading term. And I'm going to show you why this works the way it does, but first let's put it into practice. So first we're going to list out the factors of the leading coefficient and the factors of the constant term first. So we have this quadratic equation. Now the factors of the leading coefficient for 21 would be 1 and 21, as well as 3 and 7. But now when you multiply to get 21, it could be positive 1 times positive 21 or negative 1 times negative 21. So we'll just put the positive or negative of either of those numbers along with the positive or negative of 3 and 7. So these are the factors of the leading coefficient. Now the factors of the constant term, 10, they're going to be 1 and 10, or 2 and 5. And again, I put that plus or minus because they could both be negative. Now, what it means for the possible rational roots for this equation would be the factors from the constant term over the factors of the leading coefficient. So I'll methodically go through. I'll put 1 over all of these numbers in my leading coefficient. So I could have 1 over 1. I could have 1 over 21. I could also have 1 over 3 and 1 over 7. And again, I could have used positive or negative of either of those numbers, so it's like plus or minus all of these numbers. And I'm going to do that for every single one. Now, to simplify, this 1 over 1 is just 1. So plus or minus 1, plus or minus 1/27th, plus or minus a third, and plus or minus 1/7. Now I'll put 10 over all the numbers. So I'll plus or minus 10 over 1, which is just 10, plus or minus 10 over 21, which cannot be simplified, plus or minus 10 over 3, plus or minus 10 over 7, and none of those fractions could be simplified any further. And now we continue to do this for all the combinations. So now I'll put 2 over all the leading coefficients. So plus or minus 2 over 1, which is just 2, 2 over 21, 2 over 3, and 2 over 7. And then lastly, plus or minus 5 over 1, 5 over 21, 5 over 3, and 5 over 7. So of all the possible rational roots, these are all of them. There are no other rational roots that could possibly exist, meaning 3 is not going to be a solution to this equation. Now, why is it that these are the only possible rational roots? Now, whenever I factor a polynomial, in this case, this expression factors into 3x plus 2 and 7x plus 5. So give me 1 second to write that down. So 3x plus 2 and 7x plus 5. And when I go to set these equal to 0 and solve, they give me two solutions, which would be negative 2 over 3. So negative of 2 over 3. And that one gives me negative of 5 over 7. And what's really convenient is that the numerator of all those answers was a factor of the constant term, and the denominators of both the answers were factors of the leading coefficient. And you can kind of see that in the linear factors, the plus term at the end was always on the numerator. And when those are all multiplied together, they give me that constant term. And then 7x and 3x, when those are multiplied together, that give me the leading term. And those numbers in front of that were in the denominator of the answers. So that's why this theorem works as well as it does. Now let's use it in practice to solve an equation. So let's say we're going to use the rational root theorem to first list all possible rational roots for each equation, and then we're going to find those rational roots. So looking here, what are the leading coefficient factors? Well, for 15, we know it's 1 and 15 and 3 and 5. So I'm going to list all of those numbers out. And all the constant term factors are just 1 and 2. So all the possible rational roots would be all of the constant terms over the leading coefficients. So I'll have plus or minus 1 over 1, which is just 1, 1 over 3, 1 over 5, and 1 over 15, as well as plus or minus 2 over 1, which is 2, 2 over 3, 2 over 5, and 2 over 15. And you saw earlier that 2/3 and 5/7 were both part of that list. So here, only these are the possible rational roots. So we can actually just start testing. So I know 1 could be a rational root, so I can just plug it in and see what I get. So you get 15 times 1 minus 30, 15 times 1 cubed minus 32 times 1 squared plus 3 times 1 plus 2. Adding up all of this together gives you negative 12, which is most certainly not 0. So this is not a root of the equation because I didn't get 0. But I could try another number. Look at my list. 2 is also a choice. I could plug that in. So I get 15 times 2 cubed minus 32 times 2 squared plus 3 times 2 plus 2. And that would be 15 times 8 minus 32 times 4 plus 6 plus 2. And in this case, this does add up to give me 0. So that already tells me that this is a 0 of the polynomial. To find more solutions, the factor that comes with that is x minus 2. And I can actually factor that out to find the other remaining factor with it by using synthetic division. Meaning if I divide my polynomial up here by x minus 2, I can find what the other factor that goes along with it is. So I'll put 2 up in this box, the opposite of that sign, fill in my coefficients. So 15, negative 32, 3, and then 2. Drop that 15. 2 times 15 is 30. Negative 32 plus 30 is negative 2. 2 times negative 2 is negative 4. 3 plus negative 4 is negative 1. 2 times negative 1 is negative 2. 2 plus negative 2 is 0. It definitely is a factor. And I'm left with 15x squared minus 2x minus 1. So I found that other factor, and now this is just a quadratic, so I can go ahead and factor that one as well. That just requires us to find the number that multiplies to negative 15, which is a times c, adds to negative 2, which would be negative 5 and 3. So I have 15x squared minus 5x plus 3x, then minus 1. Use grouping, and I'll get x minus 2 times a 5x comes out of that first group, leaving me with a 3x minus 1. The second group already is 3x minus 1, so I end up getting 5x plus 1 times 3x minus 1. So I've fully factored my equation, and I use these possible rational roots to help lead me. And all my solutions will be x is equal to 2, which was the first one I found, negative 1/5, and positive 1/3, all of which were possible solutions I saw over here. So it's really nice how you can use a rational root theorem to get you started, and you can start like just checking and testing to see which ones can work. Let's try it one more time. So we see here we have 2x cubed plus x squared minus 7x plus 6. The factors of the leading coefficient are just 1 and 2. And the factors of the constant term are 1, 2, 3, and 6. So all my possible rational roots would be 1, my constant term, over both my leading coefficient factors, so 1 over 1 and 1 over 2. So it's 1 and 1/2. 2 over 1, which is 2. But then 2 over 2, which is just 1. So I don't need to list that one. That's redundant. And then 3 over 1, which is 3. And 3 over 2. And then 6 over 1, which is 6. And then 6 over 2, which is just 3. So I don't need to put it again. So these are all my possible rational roots. And another way you can test to see if it is a solution is to actually use synthetic division. Since we learned with the remainder theorem, if it's equal to 0 at the end, it's a factor, and it kind of leads you to figure out what zeros are in the function. So let me just try using synthetic. I'll start with 1, and I'll divide my polynomial. And again, that 1 comes from the factor x minus 1, so keep that in mind when we go to factor later. So the coefficients of my polynomial are 2, 1, -7, and 6. So bring down the 2. 1 times 2 is 2. 1 plus 2 is 3. 1 times 3 is 3. -7 plus 3 is -4. 1 times -4 is -4. 6 plus -4 is 2. There is a remainder. It's not 0. It's some other number. So 1 doesn't work. And it is plus or minus 1, so we could try -1. Use those same coefficients, so 2, 1, -7, and -6. Oop, just realized the mistake I made over here, but luckily I didn't change my answer. That would be -10 at the end instead of -2. But that doesn't quite work. So now over here, I bring down my 2. -1 times 2 is -2. 1 plus -2 is -1. -1 times -1 is 1. -7 plus 1 is -6. -1 times -6 is +6, and that gives me a 0. So this quadratic I end up with after I divide, 2x squared minus x minus 6, is one of the factors of my polynomial, along with x minus -1, which is x plus 1. So I can factor that polynomial to be x plus 1 times 2x squared minus x minus 6. And again, I'm looking for two numbers that would multiply to -12 but add to -1 to help me factor further, giving me 2x squared minus 4x plus 3x, which those multiply to -12 and add to -1. And then I can factor out the common factor. So between 2x squared and 4x, they have a 2x in common, leaving me with x minus 2. And then the second group has a 3 in common, leaving me with x minus 2, which is my other factor. And setting all those equal to 0, I can get -1, -3 halves, and 2, all of which were listed above. -1, -3 halves, and +2. So we've predicted those rational roots. And if they weren't in this list, they would have had a square root or an imaginary number in them. And that is how you use the rational root theorem.